Halo, Kang Rija.
Halo Kang Adit.
Ya, sehat, Kang.
Alhamdulillah sehat.
Kita tunggu ya kira-kira 5 menit lagi ya, Kang ya. Melihat
Siap.
yang daftar sih udah 60-an, yang mudah-mudahan yang online juga sekitar segitu.
Siap, santai.
Halo, Profesor Thierry Mare. Prof. Thierry, how are you?
Hello, I'm fine.
Are you in Jakarta?
Yes, yes, I am in my office.
So, maybe your session is around 4 o'clock.
4 o'clock, you mean? Okay.
The first speaker is Dr. Riza from Bandung Institute of Technology. Okay. And the second speaker is Mr. Sampo Tukanen from Finland.
Okay.
So around 4 o'clock.
Okay.
It's your session.
Okay, no problem. I will wait.
Okay, thank you, Prof. Kang Reja, kita bisa mulai, Kang?
Oke, siap.
Oke.
Wah, ada Disan nih.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good afternoon for all participants and for the speakers. I'm happy this afternoon because we will have 3 speakers from different nationality. The first speaker is Dr. Riza Wirawan from Department of Material Engineering at Bandung Institute of Technology. And the second speaker is Mr. Sampo Tukanen from Tampere University in Finland. I hope he will join with us soon this afternoon. And the last speaker, it's an honor for us, for our department, that we have Professor Thierry Mare, the head of collaboration department, I think, for science and technology at French Embassy in Indonesia. Glad to see you, Prof. Thierry. So for this first session, I will invite Dr. Riza Wirawan. You can share your presentation, Dr. Riza, please.
Okay, wait.
So you will have around 45 minutes for the presentation and maximum 15 minutes for the question and answer. So please, Dr. Riza, you can start.
Okay, thank you, Mr. Aditya, and very good afternoon, everyone. So I'm here to present about the natural fiber composite materials, and my name is Riza Wirawan from Research Group of Materials Science and Engineering, Faculty of Mechanical and Aerospace Engineering, Institute Teknologi Bandung. So without further ado, I will start the first presentation. Okay, this is the outline of the presentation. The first, I will introduce you about the composite. I will introduce you about the composite materials, about the definitions, about the history, some variation of the composite materials, and also we will discuss about the highlighted properties of composites. And also after that, we will discuss about natural fibers and their composites. So what I will share about this afternoon is I will discuss about the fiber sources, the matrix, and the applications. And also at the last of the presentations, I will present my last research on natural fiber composite materials, which is the sugarcane bagasse and polyvinyl chloride or PVC composites. So let's start with the definitions. So as per definitions, the composite materials can be defined as a combination of 2 or more materials that result in better properties than those of the individual components used alone. So when we talk about the combination of 2 or more materials, we also have some alloys. Some metal alloys also combination of 2 or more materials. But in the composites, it is specific to the that the properties of each materials will retain its separate chemical, physical, and mechanical properties. So different from alloy, when you add some carbon to iron, for example, the carbon will dissolve in the iron. So they will produce, or they will form some solution, ferrite or pellet, or yeah, maybe anything else. But for the composite, we will see each of the materials as it is. Okay, so these are the examples of the composite materials that we can see every day. Yeah. For example, if you like to play tennis, long time ago, the racket were made of wood or maybe some aluminum. But nowadays, you may have some carbon composites, yeah, carbon and some polymers for making these rackets. Yeah. And then if you have a chance to see the inside of the rackets, you will see some fiber inside. So the fiber is still have the physical and mechanical properties as the fiber before it composed to the before it make the composites. Yeah. And also nowadays, if you have a bicycle in nowadays, the expensive one, you will have the carbon fiber also inside. And beside the expensive stuff, you will also find some composites for the chair, yeah, for the seater here. If you have maybe see inside the Metro Mini in Jakarta, you will have this kind of chair, and if you see from the back, you will have ability to see the fiber, yeah, the fiber inside this kind of chair. And also, if you see the concrete, yeah, you can see here, these are some steels, and then the steels will be covered by the concrete, the Portland cement, yeah, and the Portland cement, and also some sands, yeah, some many particles inside. They are also the composites. Yeah. You can also see the composites inside your bathtub, and many applications nowadays. You can see many stuffs from the composites. And if you have a chance to break all of this stuff, you can see the fiber inside. Yeah. The fiber, which is the chemical and physical properties, is remain the same as the fiber when before it is made as composites. Yeah. So let's talk about the history of the composites. Actually, 3,000 and 400 before centuries, we can see some old buildings are made from straw and mud bricks. It is actually the composites because you can still see the straw inside, and also you can see the mud. Yeah, it is a composite from natural fiber actually. So from this information, we can see that actually from the before centuries, people have used the composites, yeah. But of course in the traditional way. And later on, at the 1,200 after centuries, yeah, BC before Christ, yeah, and then 1,200, we have the composite balls from the Mongolian. They make a composite from wood and bone, something like that, and also from the natural resin, pine resin. Yeah. So two of them are actually composites, but at that day, they just use the composite, that they don't know the theory inside, but because of their experience, they can make stuff from the composites. And actually, the modern composites is start at 1930s. It is because of the development of polymer. And the synthetic polymer was developed at the beginning of 1900s, yeah, at the beginning of 20th centuries. So it is following the glass fiber following the development of the polymer. So at the 1930s, people start to use glass fiber and reinforced polymer to make some composites. And then at the 1960s, yeah, after the World War, there is a development of carbon fiber. Yeah. And then they know that the carbon fiber is very high strength and also high modulus. So when they use carbon fiber to make a composite, we can have good properties that cannot be achieved by any other materials before. And at 1990s until now, we can see the modern composites. It is actually developed, more developed in every years. So many types of composites we can have now. Okay, so because as per definition, it is actually the combination of two or many materials. The composites actually have two materials inside. One is act as the matrix. The other one is, will act as the filler or reinforcement. So the matrix will glue the reinforcement to make the composite. So the reinforcement we have now, they are available in the form of fiber, particulate, and flakes. And also for the matrix, you can use the polymer, you can use the metal, and you can use the ceramic as the matrix, as long as they can bind together the filler. We can call it the matrix. So the Portland cement is the ceramic that we can use as concrete. And there are also development in the metal matrix composites, but the most usable composite, the most known composite in this era is actually the fiber and polymer composites. So the other composites, yeah, also have some developments, but the development is not, the speed of the development is not as high as the polymer and fiber composites. Yeah. So the polymer itself, we have thermoplastic and thermoset polymer. The thermoplastic polymer actually has a good ductility, so it is actually favorable to be used as the matrix of the composite. However, because of the some limitation in the production, there are thermoset polymer is more developed than the thermoplastic composites. Yeah, but however, in nowadays there are many research in the thermoplastic composites because of the good properties in terms of ductility. Okay, let's see the properties of the fibers. There are so many fibers we can use as the reinforcement of the composites. Polyethylene, e-glass, the most famous one, yeah, and aramid Kevlar. It is also famous as safety vest, bulletproof, yeah, and also carbon fiber in many form of the carbon fiber. What you can see here is they have lower density than aluminum or steel. Yeah. However, the stiffness and the tensile strength, it is actually comparable with the aluminum and steel. Yeah. And some of them are higher than two of the metals. Yeah. And then the result is when we divide the stiffness and the density, or the tensile strength and the density, we may have the specific, what we call it, specific properties. Yeah, it means that if we compare among these materials in the same mass, yeah, in the same weight, then we can see that all of these fibers, yeah, have the stiffness, the specific stiffness higher than both of aluminum and steels. And also for the tensile strength. Yeah. So if we compare, for example, 1 kilogram carbon, yeah, carbon, and then you compare with 1 kilogram of steel, carbon will have better strength and better modulus. And it means if we tend to make a material that is have the modulus of elasticity or the tensile strength the same as aluminum and the steel, with the same strength and the same modulus, the composite will have lower weight. Yeah. So the carbon in the composite will have the responsibility of the modulus and the tensile strength. And after we have the composite, the properties of the composite will depend on the fiber orientation. So as you can see here, this is a modulus at the longitudinal direction, and also the tensile at the longitudinal direction. So both are at the same direction with the fiber. So we can have some materials, some composite that have high properties at the for example, at the x-axis, yeah, but at the y-axis they will have lower tensile strength. Why? Because we have this fiber in this direction. Yeah. So this direction also we can adjust. Yeah, it depends on what properties we can have, what properties we want to have in the composite. So it is called tailorable. Yeah, you can tailor it. And then if you can see the development of the aircraft, this is the data from the Airbus, yeah. And this is the year of the first flight of the aircraft, and then this is the percentage of the weight of the composite, yeah. You can see at the beginning, there is only 5% of the composite in the aircraft, and it tends to rise and rise, yeah, because of the lightweight of the materials, yeah. And at the 2013 or something, we have A350, which have around 45% weight of composites. Yeah. And then now on, this A350 is also developed, and now we can have this A350XWB, which have 53% of composite inside the body, including the landing gear. So from the A320 here, around late of 80s, the composites start from 10%, and now we have the most material inside the airplane made of composites, yeah, because it is lightweight. So if we have this chart, density versus Young modulus, we can see that this is the composites. With the low density, they have high modulus. So compared to metals, we can see draw the line here with slope 1. So we can see the composite is one of the higher Young modulus for the same weight. Yeah. Of course, the ceramic is higher because it is very hard. Yeah, but of course, because the ceramic is very brittle, we cannot use it for some application in the craft like this, in the aircraft like this. Yeah. So next, yeah, for the next development, beside the properties of the materials, high tensile stress, high tensile strength, high modulus, etc., some environmental issues also make some researchers to have some development to find other source of the fiber. Yeah. So now on we have the glass fiber, carbon fiber, all of them are from synthetic material, and they are used for high quality applications. You see that the price of the stuff from the synthetics materials are very high, very expensive. So now some of the researchers start to have some research in natural fiber. Yeah. So what is the natural fiber? Yeah. So natural fiber, we can see, we can get it from some animals. Okay. So this is not the sound sheep, the sheep. Yeah. What I mean is this is the wool. Yeah. You can get the wool from the sheep. Yeah. And then you can have silk. Yeah. And also speed rain silk. Yeah. From the spider. Okay. These are the fiber sources you can get from some animals, and you can also get some fibers from minerals. Yeah, we long time ago, many of our houses are at the top of our houses. We can get some asbestos. Yeah. However, because of some environmental and health issue, it is actually now has been banned, yeah, in many countries, because it's very small part here. You can when you breathe, you can get, yeah, these materials can get it into your lungs, so it will be dangerous for your healthy. And now the focus on our discussion is actually the natural fiber from the plants. Yeah. Why? Yeah, because of some environmental issues. Nowadays, many people use woods. Yeah. And woods and timbers are from the forest. You will have to wait couple of decades to have some woods. And you cut it, and then you have to plant in, and then you have to wait until 10 or maybe 2 years to the plant to grow up. And for at the time it has trouble, it made the problems for the forestry. Yeah, so the forests now are gone. Yeah, so timber and wood is more expensive. But some other plants are actually have some fiber inside, what we call as cellulose, and we can use it as the fiber in the composite. So we will have some alternative material of woods, and also some alternative material of some polymers. Okay, so these are some examples of the carbon fiber from the plants. You know, the cotton, and then this is the flax fiber, the most famous one for the carbon natural fiber composite, and bamboo. Yeah, you can also use the fiber from bamboo as the natural fiber for the composite materials. And actually, from the plant fiber, you can have the wood. Yeah, but of course, we don't. Yeah, we actually use wood for the composite, but some woods that you usually throw away. Yeah, some cheap wood, or maybe the powder. After you saw the wood, you have the fiber, and then the fiber, you can press it, and then you have some new materials. Yeah, and then you can also get the fiber from the stem or bast. Yeah, the example is the flax, jute, kenaf, yeah, and rami. Also from Indonesia, we have so many rami fibers. And also some leaf, you can obtain the fiber from some leaf, from pineapple, banana, yeah, abaca, sisal, and also the coconut, yeah, coconut, yeah, the seed of, or the fruit of the coconut. You can also get it from the palm oil, yeah? and also from the grass type of the plants, just like bamboo and ties, etc. So there are many types of plant fibers that we can use for the development of composites. Of course, because Indonesia is tropical countries, we have so many variety of these fiber sources. So the development is still widely open for these natural fiber composites. And this is some application we can see in nowadays. Yeah, if you have if you can see some of these cars, the interior of the cars are made of the carbon fiber and the composites. Yeah. And also so many panels now are made of composites. Yeah, instead of the plywood, you can also find the composites here. And some toys also you can have from this type of the composites in the front end of a train, and these are the flex fiber in the catamaran of the boat. Yeah. Okay, now let's see the comparison of properties of the various fibers. So the flex fibers actually now on is the leading natural fiber composites in the application because of the higher specific modulus among other fiber, including glass fiber. So usually natural fiber is compared with the glass fiber, yeah, because the strength is actually in the middle, not as high as the carbon. So there is no tend to compete carbon fiber for the natural fiber, but we can compare it with the glass fiber. And then this is the data we can get from 1999. And now at 2020, you can also get so many people explore the fiber from many sources. Yeah, but until now, we can see that the flex is still obtain the higher tensile strength and also higher modulus. Yeah, some of the fiber also try to compete the flex fiber. Yeah, but still at the application we still not yet to be compete with the flex fiber. Yeah. Okay, and then beside the fiber, we will also have this various matrix. So the matrix we have also in thermoplastic and thermoset. Yeah, this is for the petrochemical base or the synthetic matrix. Yeah. But now on, because of the environmental issue, also we have the bio-based matrix. Yeah. So the bio-based matrix is favorable to be mixed with the natural fiber because of the same characteristic it in the hydrophilic properties. Hydrophilic is that they tend to absorb water. Yeah, we use natural fiber which is plant fiber, which is absorb water, which absorbs water. So it will be better mixed with the bio-based material, which also absorb water. Yeah, so they can bind together. Yeah. However, because of the low mechanical properties, this kind of the bio-based material is still in the development. So we still have so many petrochemical-based matrix here. Thermoplastic and thermoset, we have polyethylene, polypropylene, polystyrene, polyvinyl chloride. Yeah, and then for the thermoset, epoxy, polyester, and vinyl ester and phenolic. Yeah, so of course, other than these materials, we may also have any other polymer. This is only the examples. So now let me present my previous research. So because of the properties of the natural fiber and then the environmental issues, we try to find a new composite materials which comes from sugarcane bagasse. What is sugarcane bagasse? Sugarcane bagasse is, or sugarcane is a plant that where you can get sugar, yeah, and then after you get the sugar juice from the sugarcane, you will have the bagasse, and it is actually you will throw away the bagasse. Yeah, you don't use it because if you use it as maybe the fuel, the energy is actually low energy compared to any other wood. So people tend to people try to use this bagasse to be used as any other materials. So we try to mix this sugarcane bagasse with the polyvinyl chloride. So our the next presentation is actually we can get it from some of these publications, and this is just the resume of this publication. So if you want to learn more about this composite, you can read these publications. Yeah. So the first, what is the PVC? PVC is this is the structure, the chemical structure of the PVC. So this is the vinyl, and you have this chloride here. Or if you draw it as the 3D model, the black one is the carbon, the white one is the hydrogen, and this is the chlorine. Yeah. From this figure, we can see that the chlorine is very big. So that's why actually at the vinyl chloride, actually we have fixed 56% or around 57%. The sources of these materials is actually from natrium chloride and of course the hydrocarbon. But because of the higher source of the non-hydrocarbon, so the price is very low. This is the reason why we use PVC. It is low cost, easy to fabricate. That's why you can get some pipes in your home with made of PVC. Your playground also made of PVC, and at overseas people use PVC also for the fence. And this is the comparison price of the PVC. It is lower than other thermoplastic. It is obtained in 2009, but as the comparison in this year is also not not so different from this. Yeah, but there are so many disadvantages of also from the use of the PVC. But if you don't use PVC, it is also will make a serious problem to the society. So we try to make more general use of the PVC with the addition of the fiber. We hope that the content of the PVC is reduced. So this is why we use the PVC. Bend PVC will not be the good solution. Yeah. So this is the alternative. I think I have to move a little bit fast. So this is the sugarcane you can see in the market. Yeah. So we will have the outer part, we call it rind, and the inside part we call it pith. Yeah. What you have see here is the pith. Yeah, very soft materials. Yeah. Actually, they have the cellulose, but it is not so high. Yeah, only 35 until 40%. Okay, why sugarcane bagas? Yeah, actually, yeah, because it is a trash. We want to use the unused material to be some useful materials. Yeah, this is some potential application. Yeah, before this we use it as from the PVC, and we will have. We dream to have this kind of material from these composites. So there are many challenges for these materials actually, pith, rind, the compatibility, how is the effect of history, how is the recyclability of these composites regarding to the environment. Yeah. So I think I will not to be detailed on this, but this is what we have done in the previously. So how can we make the composite from this fiber? First, we can dry the fiber under the sun, yeah, under the sunlight, and then we chop the fiber. Inside here, there are so many knives.
Sorry, Dr. Riza, I'm sorry. You have 5 minutes more.
Yeah, of course, yeah. That's why I am here faster now. Okay. So you chop the fiber to little pieces, some little pieces, and then you mesh the fiber. Then we get the fiber to 40 mesh, and we oven the fiber to make sure that it is dry. And then we mix the fiber with this melt mixer at the 170 degrees Celsius at 15 minutes, and then you will have these granules. Yeah, and then we compress it at the same temperature, and then we will have this kind of plates. Inside here are the fibers. You can see the different color. It is because of the different content of the fibers. And then we cut it to the standard of the ASTM for the tensile test. Yeah. So before that, of course, we test the single fiber to see the potential, and then we can see from here the Young modulus of the rind, the outer part, is much higher than the inside part of the sugarcane bagasse. And then also the tensile strength. But for the maximum strain, the pith or the inside of bagasse is higher, a little bit higher than the rind. So what we have here is actually for the tensile strength, if you have the rind, the outer part of the composite, the outer part of the sugarcane bagasse, we will have higher strength than the PVC, higher strength than the PVC, higher tensile modulus of the PVC. But for the pith, it is lower than the PVC itself. Yeah, but it is lower in the impact energy because of so many gaps here. You can see it is obtained from the SEM, scanning electron microscopy. There are so many gaps here, so the gaps will produce the cracks, and then we'll have some low impact energy. Yeah. So I think I will skip. Okay. So the most important one is actually we try to have some treatments to this fiber to have so more better properties. But surprisingly, when we don't wash the sugarcane bagasse, we will have higher tensile strength and higher tensile modulus. Why? Because there is sugar inside the bagasse, and the sugar actually have responsibility to higher the tensile properties of the composite. This is the surprising result from this research. Yeah, so you can see this is the unwashed material. It means there are many fibers here. This is the treatment with the other chemical. You can see the morphology, the structure is not so different. Yeah, we can see if you use the B, C, and D, there are many void inside. But for two of these, they are better in mix. Okay, I think I skip this one, but this is actually how we try to recycle the composite, and at the for the conclusion, we can recycle this composite at the, and then we can get the tensile properties are not significantly changed after the cycle of the composite. Okay, I think that's all because of the time. And then this is the conclusions. We have the best tensile properties at 40% of the RIN and PVC. And yeah, actually we also test the thermal stability, and it offers higher thermal stability. And this is the surprising result. It is the best treatment. It's not treatment because you have the sugar inside, and sugar help you to have better tensile properties of the composites. And then if you have the thermal history, you can remove the thermal history by reheat the composite, just like when you have the thermal treatment or heat treatment of the steels. Yeah, just like the steels, you will have the heat treatment also for this composite. Okay, thank you very much. If you have any questions, you can email me. Both are the active email. You can choose any of those emails. Thank you very much. So maybe there is any question. So I give it back to you, Mr. Aditya.
So thank you, Dr. Riza Wirawan. So please, for the participant, you can ask directly to Dr. Riza if you have any question for him.
Boleh bahasa Indonesia juga. Saya masih bisa bahasa Indonesia.
Ya. Yang ingin berbahasa Indonesia silakan. Mungkin dari saya dulu Kang ya, sambil menunggu pertanyaan.
Silakan.
Nah, itu pertimbangannya di treatment, di surface treatment itu pahami surface dari apa namanya fiber dan PVC-nya kan harus kompatibel ya. Nah itu pertimbangannya seperti apa Kang?
Ya, betul. Jadi memang secara umum kalau Anda punya carbon fiber dari serat dari natural fiber, ini suara saya ini ya apa? Mantul ya. Oke, jadi secara umum natural fiber itu dia tadi hydrophilic, jadi dia menyerap air dan dari segi kimianya dia akan lebih mudah berikatan dengan yang hidrofilik juga. Nah, masalahnya polimer itu kebanyakannya termasuk PVC ini dia bersifat hidrofobik, dia takut akan air. Sehingga kalau kita temukan betul-betul langsung antara polimer, natural polimer, cellulose dengan si komposit tadi, si PVC tadi, dia tidak akan menyatu, ya, susah untuk menyatunya. Itulah kenapa si surface-nya, si permukaan si fiber itu harus kita atur lagi atau kita modifikasi. Nah, modifikasinya banyak. Ada yang menggunakan tadi alkali treatment, ada yang menggunakan ya banyak senyawa kimia yang bisa digunakan untuk membuat dia lebih kompatibel dengan PVC itu. Nah, yang mengagetkan dari hasil penelitian ini adalah kita sudah mencoba bukan semua sih, beberapa senyawa untuk membuat kompatibilitasnya lebih baik. Sampai ada yang paling baik itu adalah PMPPIC. Tapi ternyata begitu kita bandingkan, kalau dibandingkan dengan material yang sudah kita cuci, memang lebih tinggi gitu ya. Tapi begitu kemarin dicoba, coba kita tidak cuci gitu ya, ternyata gula itu sendiri cukup membantu untuk meningkatkan kekuatan tariknya. Dan pada akhirnya dibandingkan kita beli yang mahal-mahal gitu ya, ternyata dengan membiarkan ada gula di sana pun sudah cukup untuk membuat dia berikatan dengan baik dengan PVC itu. Gitu. Jadi usahanya kita sudah coba dengan menggunakan berbagai macam senyawa kimia, tapi pada akhirnya ternyata dengan gulanya sendiri sudah lebih baik.
Oke. Terima kasih Kang. Ini ada satu pertanyaan dari Miftahul Jana. Hello Mr. Rija. My name is Miftahul Jana. If we see in Miracle of Fiber table, there is comparison between metal fiber and the plant fiber. I realized that the plant fiber composite have different method that we use in calculating the tensile strength and elongation of the metal and plant fiber composite. Is it apple to apple, sir, to compare since these two types of fiber using different ASTM number?
Yeah. Okay. Yeah. Of course, if you want to compare in detail, yeah, it is not apple to apple. Yeah, and then after that, you can see also if you have this steel in the form of the fiber, yeah, you can also have the steel have the higher tensile strength and higher tensile stress as compared to the steel in the bulk form. Yeah. However, it is also we are not comparing between the carbon material or the glass material and the steel, yeah, but we compare also the form of the material. So with this method, we can also know that if we have a fiber, yeah, if you compare the fiber with the bulk material, the fiber will have higher tensile strength. Yeah, but you can see the difference is so high, so we can also make sure that the fiber have higher tensile strength and the elongation. Yeah, of course it is not apple to apple, but we compare. When we compare, we can see the trend. Yeah, the trend, when we compare, the difference is very significant. So we sure about the result. Yeah. So we see about the result with single fiber. Then how about woven fiber? Okay, woven and single fiber is different in terms of the fiber direction. So if you have this single fiber, it means 100% the direction, 100% of the fiber is directed to one angle. But if you have the woven fiber, and then you have half of the fiber in the direction of the x-axis and the half of the fiber in the direction of the y-axis. So in terms of fiber fraction, if you have unidirectional fiber, you will have 100% of the fiber will have the tensile strength of the fiber will have the responsibility to the tensile strength of the composite. But if you have the woven, so more or less only 50% of the fiber will contribute to the tensile strength of the composite in this direction, x direction. But in y direction, of course, the woven will also help the tensile strength of the composite. Yeah. So it is not better or worse, but in which direction you want to have this composite in higher mechanical properties. Yeah, that's why we call it tailorable. Yeah, if you want to have in x direction only, use the unidirectional, the single fiber. If you have if you want to have strength in the x-axis and y-axis, you can use the woven. Yeah.
So,
Oke, untuk proses manufaktur.
Oh iya, Kang. Bagaimana?
Ya, sorry, saya baca langsung aja ya, biar cepat ya.
Ya.
Ya. Bagaimana Pak campuran homogen antara natural fiber dengan matriks? Nah, natural fiber itu bentuknya kecil-kecil. Nah, kecil-kecil sehingga begitu kita panaskan, yang tadi ada internal mixer itu ya kita mix ya, sama seperti Anda membuat mixer untuk adonan kue gitu ya. Jadi kita mix ya dengan waktu tertentu. Biasanya ditandai dengan kalau dalam menghitung reologinya gitu ya. Begitu dia sudah reologinya tetap, maka kita anggap dia mixnya sudah bagus. Silakan Pak Aditya. Masih mute ya?
Ya. Terima kasih Kang. So, thank you very much, Dr. Rija, for the answer. Because limit of the time, we have to complete the first session. Thank you very much, Dr. Rija, for the good slide to us by email, because the participant will receive this slide and also the electronic certificate.
Okay, thank you everyone. Good afternoon.
Thank you very much, Dr. Rija Wiran. So we will move to the second speaker. I'm not sure, do we have Mr. Sampo Tukanen here?
Yes, I'm here.
Hello, Mr.
Hello.
Sampo. Okay. So how are you, Sampo?
Yes, I'm fine.
Fine. So it's
Yes,
so
I'm
it's
good. There's some delay. There's some delay in the in the Zoom session because I hear my voice after a few seconds later. but
so,
it's okay.
So for all the participants, Dr. Sampo, we met in Paris, in Saclay a few years ago, and we work at the same institution at Saclay. So I'm happy to see Mr. Sampo Tukanen, PhD, to present his work about piezo sensor, I think. Yeah, it's a bio-based piezoelectric sensor material. So, Mr. Sampo, the screen is yours. Please, you have 45 minutes for the presentation and 15 minutes maximum for the question and answer. Please.
Okay, thank you, Aditya. I thank you for this invitation. It's very nice to have to participate to your webinar. So nowadays I'm working at Tampere University in Finland, and as an associate professor at the moment. And I've been for a few years I've been studying this nanocellulose materials and they use it as a piezoelectric sensor material, which is like piezoelectric materials are conventionally, they are not bio-based, but they are some kind of crystalline materials from metal oxides or something else, or fluoropolymers. So this is basically, we are aiming towards the bio-based alternative solutions to find some new materials which can replace the new the conventional piezo materials with some disposable and bio-based materials which would not harm the environment so much, and they could be kind of if you want to make basically like trillions, and there's this vision of like trillion sensors. If you want to put sensors everywhere, then you have to have them kind of disposable or environmentally friendly, because they would otherwise harm the environment too much. So this is basically the motivation for this. Okay, I will. Okay, how this works? Let me see. Okay, so first I will talk about the how different types of cellulose we have studied. Then I tell about the film fabrication, and then some basics of the piezoelectricity, and the last, the results what we have obtained with these sensors we have made. Okay, first introduction to nanocellulose. Okay, here I show the how can you make actually the nanocellulose from wood. So first here on the left you can see the wood cellulose fiber, like conventional fiber taken, dissolved out from the wood. You take this cellulose fibril from that, and then what you can get from that is this kind of fibril where you have crystalline regions and amorphous regions. Then you can, when you use mechanical sharing and some maybe chemical pretreatment, you can obtain cellulose nanofibrils. And these cellulose nanofibrils are like CNF, called also as CNF, and they are about the diameter from 5 to 30 nanometer about, and they can be length of over 1 micrometer or even longer. And if you want to go on from this, you can use some chemical treatment called hydrolysis with some strong acids. You can get rid of the amorphous areas, and you can end up into these only these crystalline areas, and these are called cellulose nanocrystals, which are about diameter of from 2 to 20 nanometer, depending on the source and on the treatment, and the length is about some hundreds of nanometers. And these are also called nanowhiskers sometimes, but now I think nowadays people don't use these nanowhiskers anymore, but more of these CNC. So cellulose nanocrystals is more frequently used term here. Okay, so this is what you can make from wood. Then also we have studied another approach, because there are some bacteria. Oh, let me see if I can remove this one. Okay, yeah. So there's another way to produce kind of nanocellulose material films. There are some bacteria which are producing cellulose from using the polysaccharides as a source material, like as a cellulose source, basically. So normally they use glucose. So here I have this in picture. We have made, like, put some sugar to the cellulose, and then with the fermentation they produce this kind of film type structures. And when you try these films, you can prepare this kind of freestanding nanocellulose films. Okay. So then I go more in details to this film fabrication. So about this wood-based materials. So how this CNF, cellulose nanofibril material, was obtained. So we have used mechanical homogenizing process. So we have basically used 6 passes with this microfibrillator equipment, and started from this bleached birch cellulose mass, which is conventionally used as a when you want to make a paper like conventional paper, you start from this mass basically, but then here in this case we use this microfibrillator to make it smaller, to separate the fibrils from each other. There's a reference here for the paper basically describing the technology. And then we, after this, when we got the basically nanocellulose out from this mass, then we used the pressure filtering to try the mass to the film, remove the water, and then we use the hot press to compress to make the film kind of stiffer and kind of get the extra mechanical properties and make it more like dense with this. And what we ended up with this about 45 micrometer thick CNF film here. And this, because in this case we have used the CNF gel as a starting material. It contains both the crystalline and amorphous areas in the film. And here we have some images. You can see the surface SCM image of the surface of the CNF film, and then below you can see the cross-sectional film. So you can see some layering of the films, because there's some self-alignment of the cellulose, because it has lot of like van der Waals forces and hydrogen bonding between the other fibers, so it forms this kind of layers because of that. Then the other case with the bacterial cellulose. So we have, in that case, we have studied the natural bacterial strain, which is called like white type bacterial strain, but we have also studied 3 different like engineered strains where they have modified the genome of the bacteria so that it can produce kind of the aim here was to enhance the production of the cellulose by engineering the modifying of the strain genome. And these are called here like here this PA, PAB, PABCD. I'm not expert with this because I'm a physicist, and this was done in collaboration with the chemist who was actually doing this engineering. So you can see more about this engineering from this paper. On the below left you can see the reference of that, but we obtained some significant differences in the production rate of the cellulose of the nanocellulose film with this engineered strains in comparison to this wild type. Just as this VT means wild type, so it's a natural cellulose strain. Okay, and there are some SCM images of these different of these bacterial cellulose films produced by different methods. The films are about from 5 to 10 micrometer thick, and you can see in this SCM image on the left, you can see the cross sections this looks a little bit different than the wood-based cellulose films, which I previously showed you, but they are quite homogeneous. But there's also these, you can also see this layering formation here, as you saw in the wood-based nanocellulose case. And there are some top view figures as well. And then after this film formation, we also measured the crystallinity level because for the piezoelectric sensors, the crystallinity was an important factor. So we saw some differences of the crystallinity, and here you can see in this table, you can see the film thicknesses, and they varied a little bit from 5 to 10 microns, and the crystallinity is quite high. It's more than 90% of crystalline areas in this case. And okay, then we go to the piezoelectricity. So a piezoelectric effect means that you have, like, when you apply a mechanical force to some material, it creates an electrical charge separation. So you can create electricity from mechanical force, basically, or mechanical signal exposure, I mean. And based on the theory, there's this piezoelectric tensor matrix which you can define, and it's determined by the symmetry of the crystalline lattice. And in this case of cellulose, this is cellulose crystal is kind of monolithical C2 symmetrical structure. And when you take into account some cancellation effects in the theoretical formulation, you end up with this kind of DMN matrix where you have only two components which are not zero, this D14 and D25, which are like D14 is minus D25. So this theoretical tensor was predicted already like 1955 by Fukada in Japan. And after that, it has taken a long time after people have really measured these things. So this was kind of, it took like 50, 60 years from the prediction to go to actual experiments. It is quite long time, I think. And okay, that is the theory briefly, and then we go to the results. So what we did, we have made this kind of sensor elements where we sandwiched the nanocellulose films between two electrodes. So on the left bottom you can see this structure basically. So you have in the middle you have the nanocellulose film, either wood-based nanocellulose or bacterial nanocellulose, and then you put we have evaporated copper electrodes on PET, the plastic PET substrate, and used those as electrodes on the both sides of the nanocellulose film. And here you can see the actual sensor on the right side. And okay, this is also, I highlighted these crimp connectors here because it is one challenge of this like flexible electrodes and flexible sensors and flexible electronics in general, there's a challenge of having a flexible connectors which you can trust, because it is not conventionally done. Conventional electronics rely on the rigid silicon. You don't have anything flexible there. So in this case, we have used these crimp connectors, which are quite good. They work, so you can bend them and they still work. And there's a reference to the paper here where you can read more if you like. And there's a measurement setup what we have used for this the analyzing of the piezoelectric sensitivity of the sensors. So we have this kind of mini shaker which applies a mechanical force on the sensor, and then we have a force sensors. We have a static force sensor and the dynamic force sensor in the device, in the system. I mean, and then we placed the sensor on the horizontally on the metal plate, and then we apply the force on that. And in this kind of setup, we measure basically the normal force, how the normal force is applied on this sensor element, and we measure the output. So this is closely related to the coefficient D33. This is like the piezoelectric coefficient what we are basically studying. I have to mention there are also these other coefficients which are a little bit messing up the picture here, because we cannot say for 100% that we are only measuring D33, but there are always some shear forces and other which affect this. So we cannot say that we are only measuring D33, but this is most like theoretically that's the case. Okay, and here you can see on the right up, you can see the real actual setup. So there is the plate and the sensor, and there is a shaker head. This on up here, you can see the shaker with the sensors, measurement sensors. So we applied first. We have to apply some static force. So we have used 3 Newton static force, which keeps the sample at stage, so it doesn't move around. And then after this, we apply this sinusoidal dynamic force, which have to be, this dynamic force has to be less than the static force, because otherwise we would detach the sample from the state. So basically, yeah, basically we are just changing the pressure we are applying on the sensor, but still it maintains the place, the position where it is. And then we have to do statistics, of course, to have the better reliability on the test. We have done from 3 to 9 repeats, and also we have turned the sensor around from upside down to get the idea of if there are some differences between the sides. Of course, theoretically there shouldn't be, but there are, because it's not perfect. The system is not perfect. So basically what we get out, like sensor sensitivity, what is basically the amount of the charge we get out divided by the force we apply. This gives out the sensitivity. And the unit for this sensitivity is coulombs per Newton. And in this case, we talk about picocoulombs per Newton because it's like generally used unit for the basically this picocoulombs, because that's the scale what you get in normal piezo materials. So that's why there's this pico before. And here you can see on the bottom right, you can see the sinusoidal input signal, input force, and then the measured output charge from that. Okay. Then on the next slide, we have I have here the some results. So we have these 5 sensors. On the, like I talk about the table on the top right. So we have here the 5 sensors we have made, and we have the sensitivity on side 1, and then upside down turned sensor side 2, and there is also measured these error or different error defined from differences from these different positions from the electrode. So we have basically moved the we have the sensor area, we have moved the position where we apply the force, and this gives us this basically the standard deviation what we have between the different places on the electrode. Because the film is not perfect, there are some differences and some inhomogeneities on that. So that's why we have measured these with many different positions. And the average, if we compare, it's in this wood-based nanocellulose film, it's about 5 picocoulombs per Newton. If you compare these, you can compare with the commercial PVDF, which is the fluoropolymer film, which is quite expensive and not disposable and not bio-friendly. So this PVDF gives something close to 30 picocoulombs per Newton. So, okay, we are not there. This is like almost 10 times lower the value what we got from these films. But anyway, it works as a sensor material. And then on here bottom right, you can see the plot of the like different positions on this electrode where you where we have measured these, and it doesn't vary so much. So it's, if you compare the variation of the sensor sensitivity between the positions on the electrode, it's almost about the same as with this commercial material, which is surprisingly good. Then, if you talk about the sensor, you want to build the real sensor. Some standard things what you have to measure is, one is the linearity. So you talk about basically the term is non-linearity, what you talk about. So you measure the sensor charge, this charge, this can be also sensitivity, but it can be, here is the charge output as a function of dynamic force what you apply. So basically you increase the force applied and you measure the output, and this should be linear. If you want to have an optimum sensor, you should have linear output. And here we have measured with the commercial PVDF film, and it gives quite good linearity with our film as well. And another issue with the sensors is the hysteresis. So when you go up with the increasing force or you go down with the decreasing force, how does it does it give a different output? So yeah, it could be kind of this banana. If you have very bad sensor, it can be this banana shape. But in this case, we have got quite good hysteresis curve as well. So in optimum case, it should be identical, but it's never identical because there's some like how would you say it, like a memory. The material has a memory, so it doesn't behave ideally in these cases. Then about these bacterial cellulose films, here are some summary plot of this piezoelectric sensitivity of the bacterial cellulose films, and this varied between different the bacterial cellulose films produced from different strains. And here we observe that the wild type, so this natural bacterial cellulose strain, gave the highest piezoelectric sensitivity values, which are like very high. This is almost close to the commercial PVDF values, not so far from those. And for some reason, these engineered strains gave smaller values. We don't actually understand why, but my hinge is that because this wild type, like natural bacterial strain, the growth, how it grows the cellulose, it's slower, so it has more time to align, to form bonding between the cellulose fibers and fibrils, as in this case of engineered strains, where we have like make it faster, to producing faster the cellulose, so it doesn't have so much time to align. So maybe that's one reason to, it could be one reason why it doesn't give so much sensor output when it doesn't align so well. But this is just speculation, but not officials, but it's speculation. Yeah, and it's, yeah, you can see the paper reference for the more information from that side. Oh, let me see. Okay, and also we measured for these bacterial cellulose films, we measured these with the different forces, like increasing the force. First we had 1.4 Newton force, and then we increase it a little bit, and we saw the increasing output. We don't, I don't have a plot here for the curve, but basically with these points you can make this linearity curve as well while plotting this, but I don't have it here. And then we also measured the durability. So basically how long the sensor can work, basically. So we measured it here. What is it? About 3,600 seconds. We just keep pushing the sample for a long time and measure the output, and it seems that it kind of remains its functionality for a long time. There's some in the beginning, there's some stability, and then when it goes to the certain level, it kind of remains on that. So it at least we see that the sensor doesn't die, or it doesn't get broken fast, so we can measure for a long time, which is one requirement for the sensors, so that they just work for a certain time at least. Okay, that was my that were our results. So as a summary, we have compared the piezoelectric sensor properties of these wood-based cellulose nanofiber films and the bacterial cellulose films, and they give significant piezoelectric sensitivities. In this case, these previous results we get. Sorry, sorry about, it's not corona, but it's something else. So we got a little bit lower values for these wood-based cellulose films and the bacterial cellulose films got a little bit higher. And here we didn't use any polarization or orientation, but it's only this piezoelectricity is only based on the natural orientation of the films. If you compare with the the conventional, like for long time ago developed piezo material is quartz, and it has a lot lower piezo factor than these in comparison to these nanocellulose films. And another one was this PVDF, which is commercial, very expensive thermoplastic alternative. So based on these, our results, we propose that nanocellulose is very promising material, like solution processable, renewable, and disposable material for piezoelectric sensors. And there are again the links for the publications. And then I want to mention about our recent work. We have this kind of EU funded project called BioAlu, which means like bio-based intelligence. So in collaboration with 5 laboratories in my university, we are developing different bio-based applications, and we have made this nanocellulose by ourselves in the lab. And actually we obtained, there are some recent results on this curve. If you can see, we got even higher piezoelectric sensitivities with these new films, which are fabricated a little bit different method. It's not described here, but we just made up our own method to how to make the films, and we obtained even higher sensor sensitivity values. And also in addition to this, we have used chitosan, which is chitosan is basically what you get from the shrimp, the shells. If you take it out, it's basically chitosan, and you can make that films from that also. So we have also studied the piezoelectricity of chitosan, and also we combined chitosan and nanocellulose and studied that. But I don't go to details on that. You can see the link to the publication. It was quite interesting also. And then we also we did some composite, like adding the nanoparticles into the bacterial cellulose. This was actually done by I had a visitor from Thailand for visiting a researcher from Thailand for 1 year in my group, and this publication is based on that, her work here, and it is also quite interesting. And here I just listed some people who have been working on this published work. There are people from Aalto University, which is close to Helsinki, if you know Helsinki, and then there's some people from Oulu, which is on the northern part of Finland, and people from Tampere, mostly on the bacterial cellulose side from the chemistry and bioengineering, and then there's my faculty side from these biomedical sciences and engineering side. So yeah, thank you. Do you have any questions?
So thank you, Mr. Sampo, for the presentation. So please, the participant, if you have any question to Mr. Sampo, just unmute your microphone and ask directly to him. So please. So
Oh. Sorry, I accidentally closed the slides.
it's okay. So Mr. Sampo, I think it's a interesting topic for yeah, for example, in Indonesia, for example, because we have so many resources of cellulose, and
Yeah.
when we synthesize the cellulose, for example, from micron to, I don't know, to nano cellulose, so perhaps we will get a better sensitivity of the cellulose, I think.
You mean the sensors for the sensors? Okay.
So
Yeah.
do you know if there is some result from another researcher about the difference between micron size of the cellulose and the nano size of the cellulose? Is there any big difference?
That's a good question. Okay, let me see if I can show again can you see the slide? Can you see Achitya? Can you see the slide?
Yes, I can see.
So here you can see this our new results, it's not published, but this is like this MFC. It's called microfibrillated cellulose. It's not actually the nano size, but that contains also the micro size 5 fibrils. So this film gave higher sensitivities than the actual nano size, this NFC film. So it's possible that maybe the micro size is better than nano size, but we should make more consistent comparison. Because based on this, I cannot say which one is better, but there are some publications from, was it maybe South Korea? I think South Korea, they have developed this kind of it's not nanocellulose, but it's basically conventional cellulose. They have made some energy harvesting, like bending system where you collect energy from these kind of bending cellulose film. There are several publications on that, but I think that's the only one what I have found. There's not so many research on this, so it's a new topic, I would say. So that's why it's interesting, but there's no consensus yet from this side. So
for example, this cytosan-based sensor.
yeah.
The matrix is cytosan, and the piezoelectricity material is the cellulose.
No, actually, also chitosan, because it's also crystal, it has also crystals. It's a bit it's also polysaccharide, as cellulose and chitosan are both polysaccharides. They both have the crystalline structure. So chitosan itself is also piezoelectric. But here in that paper what I mentioned here, we actually compared, we made the film with only from chitosan and only from nanocellulose, and also the mixed film.
Okay.
You can check it out. But it was the main, what was surprising was that when we mix them, the sensor effect gets lower. So the nanocellulose itself and the chitosan itself gives higher values than the mixture. I think, okay, this is just my speculation again. I think that when you mix them, they kind of, it messes up the organization or self organization of the film. I think that is one explanation, but this is also something which could be studied much more, but it was kind of interesting observation.
So we are still waiting for the question because we still have time until 4 o'clock, I think. So from the paper, the title is Carbohydrate Polymers. It's a BC nanoparticle composite sensors. BC, it's a biocellulose.
No, this was this bacterial cellulose.
Bacterial cellulose. And what is the nanoparticle?
It was this manganese. Is this manganese oxide?
Okay.
Is it correct? Manganese oxide. Yeah, like actually this Nipaporn who worked in my lab, she started from the growth of the bacterial cellulose film, and then she put this wet bacterial cellulose film there, and then she growed these manganese oxide particles so that they go inside the film somehow, forming the composite. Yeah, I'm not a chemist. I cannot say much more details about that, but it was quite high level chemistry, I say. That. Yeah, but it's quite interesting also, that results. You can check the paper. It's a new one.
Of course. So do we have any question?
Okay,
Please?
maybe I can ask something.
Okay, Dr.
Hello,
Rizal,
Sampo.
Hi.
Yeah, I would like to ask whether is there any effect of the purity of the, for example, the cellulose, the effect of the purity of the cellulose to the sensor, to the sensor effect?
Okay. We haven't studied that, but it may have effect. Actually, in this, yeah, as I mentioned before, when we studied this mixture of chitosan and nanocellulose, when we mixed two different materials, it decreased the sensor activity. So I would also assume that if you have impurities, like some other polymers or whatever animals there inside, it would decrease. But we haven't systematically studied that. So, but it should, I think we have quite high purity nanocellulose, what we have used. But let's say if we make it from the like waste material, like with the low cost materials, I think it would have an effect here. But that's very good question. If we could take some waste cellulose with a lot of impurities, how would it affect the sensor? But that's a good question. Like that should be studied maybe.
Yeah, because it is not only about the purities, but every every plants also have different different percentage of cellulose.
Yeah.
And what you have here is actually from the bacteria, right?
Problem here?
Yes.
Okay.
Yeah. So the cellulose from the bacteria will be the high purity of
Yes.
cellulose, right? Yeah.
Yes, that's a good point. Yeah. Sorry, I didn't mention that. So bacterial cellulose is high purity material because it doesn't produce anything else but the bacterial film. And it's also bacterial cellulose is used for the medical applications also because of its high purity. Because in this wood cellulose you can have some residues from lignin or whatever because it's processed from wood and it contains also other things. Yeah, it can be. Yeah, that's a good point. It can be one reason for the higher sensor sensitivities in comparison to wood based. Yeah, but that could be somehow compared also by intentionally adding some impurities to the nanocellulose to see how it affects to this. So
Sometimes the impurity also also helps. Sometimes we add the impurities.
Yeah, it depends. It depends what kind of impurity you have. If you like in this last paper we had, when you add nanoparticles as impurity, nanoparticles are basically impurity, but they enhance the piezoelectric properties. So it depends on that, what kind of. Yeah, but if you add, let's say, you add metal particles as impurity, they wouldn't help because they are conducting, and then you basically break the piezoelectric property of that. Yeah, I think this is quite new topic still. So there's a lot of things to do and research and study before the actual commercial applications. We don't have any commercial application for this.
Yeah, but you have the properties that better than the commercial one, right? Better than quartz and PVDF, right?
It's between the values are between the quartz and PVDF.
Right.
The problem with PVDF, we have previously before using nanocellulose, I have studied this PVDF. We have made these printed sensors and printed touch screen from PVDF. But then I was thinking like, okay, this is fluoropolymer, so if we make trillion sensors from PVDF, then the whole Earth will be filled with the fluoropolymer, and it's not good. So that's why I would like to go to these bio-based things.
Okay. So, do you still have any question? So, Sampo, so you said that we don't have any commercial product of this cellulose-based sensor in the market.
So far that I know, there aren't any. It's on the research stage, I guess.
Okay.
I have this one what I mentioned in South Korea. This is it EPUB, like electronic paper. you can check it out if that can be the only one which may have some commercial, I don't know, plans, but I haven't seen any really.
So maybe this is the last question before we close this this session, because okay, it sounds interesting to have yeah, for example, it's functional materials,
Yeah,
based on the let's say biodegradable materials. We
yeah,
call it cellulose. But let's imagine if before this material can do its function to sense or to be the sensor, then it's already, for example, degrade. It's already broken, for example, because the environment. So what do you think about that? Because is it okay? It is promising to have biodegradable materials, but maybe it's useless to have this biodegradable material before they can do their function, because it has already degrade, for example. It has already broken, for example.
you mean the how long it works, if it gets broken before the that's, do you mean that?
Yeah. Yes.
Yeah, it is. Yeah, that's good point, because there is it depends on the application basically. If you have an application where the sensor have to work for 1 week or 1 year, it's of course the difference that if we put the sensor on some package basically, and the package it's transferred for a few days somewhere and then it's destroyed after that, so then you don't need so high a long time to work. But if you put it to the your textile somewhere, like, then it should work for a longer time. So that's a good point. If it degrades before the end of life, so that's not good. But yeah, it depends on the application, basically.
So I think we arrive at the end of the session. Once again, thank you very much for Mr. Sampo for your presentation.
Thank you. Thanks for invitation.
We will talk again by
Yes.
messenger, for example.
Yes.
And if you don't mind, please send your slide to me.
Yes, I will send you the slides. And let's talk about the collaboration. I'm open for that if anyone is interested. So
yes. Right now I'm trying to convince some of the students to join with the research.
Good.
I will give you the news.
Yes.
So thank you very much, Mr. Sampo.
Yeah. Okay.
And bye. We will proceed to the next session. It's Professor Thierry Mare. Now he is the head of the collaboration department for science and technology at the French Embassy in Indonesia. He will talk about the research opportunities between France and Indonesia in undergraduate or in the graduate degree. So, Prof. Thierry.
Yes,
okay.
yes. Thank you very much.
Yeah.
So thank you, good afternoon. Good afternoon, everyone.
Good afternoon.
And good morning in Finland. It's a pleasure for me to be here to talk further about a short overview of French-Indonesia cooperation. So let me start by giving you some background information. So it began in 1952 when EFAO started its research in archaeology in Indonesia. Later on, in 1969, Indonesia and France agreement was made with first education and research exchange by providing scholarship. In 2009, officially agreement was created between Indonesia and French ministries, and they both providing the financial support. Then other important dates for arrangement on the field of higher education, bilateral cooperation in science, technology, and innovation. And finally, in 2019, an annual meeting between our two countries. So we have scholarships program for Indonesian who want to study in France. It's not me who is taking care of it, but my colleague Philomen. So I will show you quickly. We have a 14 scholarship for diploma to bachelor degrees. We have 8 scholarship for master level. The Islamic Development Bank and France are jointly launching a scholarship program for students applying to study in France for 5 scholarship, 1 FL scholarship for master's or doctorate, and 6 scholarships for master, PhD, and postdoctorate. In the field of Make Our Planet Great Again, it's President new scholarship. So all of this can be viewed on the Campus France website, and you can send an email to my colleague Philomen. Regarding the metallurgy on materials, we have in France 90 masters in science on materials, 172 masters in chemical and material, and 3 masters in nanotechnology. And we have a lot of masters in English language too, all over the France. About research, at the moment we have 30 double degree, 300 projects, and more than 3,500 researchers working with Indonesia. Now let's move to collaboration and citation, just to show you. At the first figure, we have international collaboration between France and other countries. As you can see, 50% of scientific paper journal in journal are made in international cooperations. On the next figure, we can also see the same ratio achieved by the Indonesian side. So let me precise the results. It's derived from the Web of Science, which take account international scientific index with journal and book chapter. It is different from CINTA index, which takes account of international journal and national journals. So when we compare to another countries, the third figure, France is on the 7th rank with a ratio of only 2.6%. But in the other hand, the total number of the co-publication is increasing. And this in all thematics. On this figure, we can see, we can see that agriculture, sustainable development, volcanology represent 50% of French-Indonesia cooperation in research. It's because it's due to the French International Research Center established in Indonesia, like CIRAD, ERD. So what we provide at the French Embassy, we connect on bridging one into another. Then after we promote and support. So we can provide 3 kinds of financial support. First one through science and impact, supporting by the French Embassy. The second is PhD Nusantara, co-funding by French and Indonesian ministries. And the third is an European program, but not managed by our French Embassy. Okay, let me speak about the PhD Nusantara. It's available from all topics, from physics, science until social science. You can see all the topics. So you can apply if you are in the topic, and material too. And this year we had new topic, innovation with the post-COVID and health, like this. Maybe it's not in your field, but anyway, that means everybody can apply to PhD Nusantara, except for nuclear, military, and defense. So we can apply from Indonesian side, lecturer are welcome to apply. On French side, it is available for all researchers from university and laboratories. The funding is essentially for mobility. From the Indonesian side, you may get additional financial support for research, but you have to go through SAME. So for French side is only for mobilities. For the mechanisms, you have to prepare a joint research proposal, same title, same content. For Indonesian researchers, you apply through SAME site. For French researcher, we apply through Campus France site. So we review and classify the projects from each side. And the Indonesian side, they provide additional research support for the project. So we evaluate and selected the best project. We match and award best project, and we publish the results. So for your information, we have selected this year, we have selected 10 projects for 2 years duration with a grant of 10,000 euros per year from the French side around. So as we can see in this figure, we have 50% chance to get it. So, okay, as you can see, this is the date, but as you can see, the deadline has passed for PhD 2021, but next year for PhD 2022, it will be around the same dates. But 2 chances to get the PhD Nusantara, by my experience, because I've got it one time before I came there, it takes 1 year to meet French partner, prepare and build a relevant 2 years research project. So the idea is to have a contact now and prepare with your partner project for the next PhD Nusantara. So, but we have another support to help you for that. It's called Science and Impact. It's a financial support supported by Federal Embassy. What is that? Okay, you can request. It's easy, simple, and flexible. You can request until 10,000 euros for 1 year project for mobility, but for conference, internship, student supervision, and whatever. If you have a partner and a new project, you can apply. You can apply. And for example, this year, we receive 68 file project with 6,000 euro average request from it. We selected 28 projects and give around 3,000 euro by project. And this for mission, networking, supervising, whatever. So if you have an idea to apply PhD in Untirta, for me you have to have a contact, French contact for a researcher. It's easy, and you can find by internet publication and citation or whatever. You make a contact. You try to build complementary project together, and you try to at the first one, if you want to meet this person, you can apply by through impact science. The date for the impact science is in January. Application you can see on the website, IFI website, and you can write to me. I can give you all the information about that. So that's the financial support we can provide for French and Indonesia cooperation. If you have any question, do not hesitate to ask me any question about that. Thank you. Terima kasih.
Thank you very much, Prof. Thierry. So, do we have any question from the participants? Please ask directly to Prof. Thierry. So maybe until we have the question from the participants, I will ask you.
Okay, so all the participants today, they are students or they are researchers?
It's mixed. It's mixed between the students, lecturer, for example.
So for the student, if you want to do a master in France,
yes,
you can see on the website from the French embassy or IFI, and you can apply to get a master grant. But just one thing, in France, tuition fees are quite cheap. For example, 1 year at university, it costs 300 euros. Okay, to apply. And after, in France, we have a lot of financial support for students. So if you want to eat, there is a student restaurant for 1 or 2 euro per meal. And if you need accommodation, there are student accommodation or social government support. So it's cost around 100 or 200 euro per month. So you can come in France with that grant. It's a cheaper compares Great Britain or US or everywhere. That's the message from from university.
So, for example, a student want to continue his or her education for a master degree, for example, in France, and of course, the students must get the, I don't know, the acceptance letters, for example, from the French higher education institution, for example. And
okay,
in your opinion, what is the best strategy to approach or to get the acceptance letters from the professor or from the French higher education institution.
Okay. If you want to go in master, for example, you have two possibilities. You want a grant, so you apply through or embassy. If you want to apply by yourself without grant, you have to go and you have to contact the university, the master, and try to get acceptance. But we can help you for that. We can contact the master and say Indonesian students want to go to this master, and if they accept, they send a letter, and it's okay. After, you have to go through Campus France to get the insurance and the real inscription, registration, and that's it. It's quite easy.
Okay. And in an undergraduate program, is there any financial support if one of our students here in our department want to take maybe 1 or 2 semesters in
Yes.
French undergraduate program?
That I show you there. It's not my field now, but I can show you there the first one. This one is for this one. This one is for license. So we have 14. We have selections. It's D3 of S1. So you can, okay, you have the calendar for registration is in May, June. And we have selections. We have selection in the IFI. There, we selected 14, the best profile.
Okay.
Yes, it's depending of the diploma you want to apply. If the student apply in a French cursus, French language cursus, we selected by the French language a little bit, but there is a lot of English courses in France, so it's depending.
So you mean with this partial diploma or undergraduate bachelor degree, I mean,
Yes.
a student can spend 1 or 2 semesters
Yes.
in a French institution?
Yes. That's it.
And it's cover all the expenses or just, for example, living or
If there is a grant, there is nothing to pay. We pay the flight ticket and everything. If you go by yourself, that I told you, registration fees are not very expensive in France. Really not compares everywhere. Compares UE, for example, in Indonesia, it's very cheap. After, what is quite expensive in France is accommodation, but government give some financial support for students. So I think if you have 500 euro per month, you can live in France if you are a student. Not if you are a professor like me, but if you are a student with the help. Yeah. So if you stay 1 year, it's the same price like fees in USA only for university, for example.
Is there any obligation about the memorandum of understanding between
no,
Indonesia higher education and
no. The first is you have to be accepted by the university before. So you have to apply at the university. If they accept, okay, you can apply for the grant. But we have a lot of connection with universities, so we can push international relation and cooperation.
Okay.
But the best, you're right, the best is to have a contact between university before, and if you get a MOU, it's easy. You can send a student as you want. In the both sides.
Oops. Whoop. What? Waduh. So, please, is there any participant want to ask a question to Prof. Thierry?
Okay, Prof. Mare, I would like to ask about the chance to have the research collaborations through PhD Nusantara, right?
Okay.
Okay. So do you have any figure how many proposals submitted and how many proposals are accepted
Yes.
in every years?
Yes. I show you the figure. This is this figure. Okay, I pass very quickly about it. At the top, do have the total of the application form. In gray is okay. In red is non-eligible. In gray is accepted. So, for example, this year for 2021, Untirta, we get 38 projects, and there is 10 project awardees.
Right.
But we have a lot of projects not mature, you know. If you take time, if you take, I think, 1 year to have to be sure your application is very good, with a planning agenda, with a student exchange, if you do something very concrete, you have a chance to get it. Not sure I have answered the question.
All right. Okay. So it means you have to have the good plan and then also the good communication with the researchers in France, right?
Yes, yes.
Before we apply.
Okay, I receive a lot of email from Indonesian, and they say, I want to apply PhD Untirta, but I have no contact. But they asked me 2 weeks before, so it's not working. We are there to connect, to have contact, but you have to speak with your partner. You have to write exactly same projects, same title, same agenda, everything together. So it's take for me 1 year to find a good project, because you need to be complementary. It's not Indonesian researcher going in France just to learn. It's complementary. Okay, but you are from ITB. That's it.
Yes, yes, I am.
Oh, there is a PhD in ITB, I think.
So there are many proposal which is eligible, but it is not awarded. Is it some points, or just because of the contact, or any other problem?
That is the application. Okay. I am not in the jury, but I have the report of the jury. So in France, and they like if there is a young student involved in the project, for example. In Indonesia, they want the high-level team, for example. So if you have a young researcher who wants to apply, my counsel is they have to make a team. They make a team with a professor, you know. But it's depending of the topic, and they are regarding how many publications do you have before, how many publications do you want to do at the end of the project. So its tech is 30 pages to write a good project. But it's a good exercise, because when you do that, I miss 1 year my project in Pesci and I win the second year, because the first year it takes time, okay, but you make good contact. It was with Yui, and after we start to work together with that PhD, because it's possible. It's possible if you have the good topic, the good complementary, you can work together. And after the second year, when I apply, we had a little publication, very small publication together with the two names. So it's good to show we know this team and we work together already. But it's not all time this case, but I think it's a good. So if you did you try to apply the patient center one time?
Not yet.
Not yet.
Just,
Okay.
Yeah.
So if you need the research laboratory contact, you can contact them. You can try to make a new project together, and after you can write something. I don't know.
All right, thank you. I think, yeah, I have some idea of the strategy. Thank you very much. Yeah.
So, thank you for the question, Dr. Riza. And I don't know, do we still have any question from the participants, please? So, I think that the French embassy, for example, maybe your position as the head of the collaboration department, the French embassy will help maybe someone or an institution that want to build a cooperation between French higher institution. Do you in the French embassy, is it possible to have someone that can help maybe my department to prepare or to build education cooperation, for example, or scientific collaboration between my department and any department in France?
Okay, so you speak about MOU, something?
Yes, MOU or any kind of support from the French embassy to create this collaboration.
We can help you. We have some MOU with university, but it is because there is a French lessons or a double diploma with our French teacher there. For me, MOU is between two universities and two laboratories. It's not, we can help you, but if you sign MOU with IFI, we cannot help you for researcher. And so you have, we can help you to connect university if you have in your mind one university or one laboratory of research, you want to make more contact, we can connect you with the International Relations Office of the university in France and write MOU. We can help you, but MOU it's between two universities for me.
Yeah, I mean the French embassy will act as a, I don't know, assistance, for example, or like a consultant in that case.
Okay, maybe you can ask Philomene for the master or stuff like that, but for the B diploma or for research that I know, if I start in my university to work with my colleague from UE in research, we wanted to send students for internship in UE. We did that. And we wanted to receive master students by our own grant in university.
Okay.
And for that, we decided to write a MOU for that, for the insurance, for the official exchange. In this way, I think.
Okay.
Because I was in International Relations Office in my university before. And when you write a MOU between two rectors from university, it's not working really because it's there is two MOU. The MOU is for the cursus, master, stuff like that, and for research. So we need the professor. It's my field, what I think.
Okay.
But
So
we can help you if you know a good laboratory, good research in the same field of you, and you want to make a professor exchange for research or education or whatever, we can help you to make contact with this university in France.
yeah, of course. Thank you, Prof. Thierry. So I think we don't have any question anymore for Prof. Thierry. Thank you very much, Prof. Thierry.
Thank you.
Merci beaucoup. And I hope we will see in the future.
Yes, we can keep in touch because when I saw the research conferences, I miss it. I can do some conferences like this about research. So.
Yeah, maybe for the next year we will have any kind of this online seminar.
Okay.
So thank you, Prof. Thierry, and for all the participants, I want to inform you about two things. The first one is next Monday, our department will have two online seminar. You can check on the chat room. In the morning, we will have speakers from NIMS, National Institute of Material Science at Tsukuba, Japan, and also the speakers from the Sultan Ageng Tirta University. It's in the morning, and in the afternoon you will see myself as the one of the speakers, and the other one is Professor Ana Barros from the Department of Chemistry in Portugal. So if you want to join, please check the chat room and complete the registration. And if you want to receive the electronic certificate and the slide of this online seminar, we will give you 10 minutes to fill in the Google form. Please check in the chat room the Google form. At the end of the chat room, you must complete the Google form in order to obtain the electronic certificate and the slides from the three speakers. Dr. Riza and Dr. Sampo have already sent the slides, and I hope Professor Thierry soon will also send the slide by email. So please, you have more or less 10 minutes to complete the Google form before we close this seminar. So I would like to thank you for all the three speakers, Dr. Riza, Dr. Sampo, and Prof. Thierry, for their contribution to this online seminar. And I also want to ask to say thank you to all the participants who joined the seminar. So I hope I can see you next Monday in the morning or in the afternoon. Thank you very much. Bye.
Oke, makasih Kang Adit.
Makasih Kang.
Bye.
Makasih semuanya. Thank you everyone.